welcome you all in this course on power plant engineering. Today we will solve a few numericals based on our previous lectures. First example is the estimated total annual operating cost and capital charges for two proposed power stations are given by the following expressions. So, there are two stations and annual cost of a station, this is station B. Annual cost of station A and annual cost of station B is given. So, fixed annual cost is 6 lakhs rupees. For B, it is costlier 7 lakh 50,000. Then capacity base multiplying factor for station A it is 3, for station B it is 5, that is known as B. This is A plus B and this one is C. Then C is unit power generation cost, that is 0.015 rupees for station A, and for station B it is a little cheaper, it is 0.014 kilowatt hour. Because the power generation is huge, so this difference also is substantial, has substantial effect on the output or total cost. Kilowatt is the capacity of the station and kilowatt hour is the annual output, right. The stations are to be used for supplying a load having a low duration curve as shown in figure. I will show you a figure, that is the load duration curve. Which station should be used to supply the base load and which should be its installation capacity, and what should be its installation capacity. So, we have to decide. This is the load curve is here, this is the load curve, this is a straight line, right. So, we have to take a combination. Suppose we take entire power 5000 kilowatt from B, right. If we take entire 5000 kilowatt from B, the fixed cost will increase, this capacity wise cost will be high. Now, if we take 5000 kilowatt from A, then this cost is going to be high, right. So, we have to find one optimum value and we have already done this, we have already carried out one derivation that we find the value of H. H is B2 minus B1 divided by C1 minus C2. If we take H here in this case, then this is B2 minus B1 and C1 minus C2. So, B2 is 5, B1 is 3, C1 is 0.015, C1 is 0.015 and C2 is 0.014, right. So, here H is equal to 5 minus 3 divided by 0.015 minus 0.014. Now, this will give us 2 divided by 0.001 or 2000. So, for minimizing the cost of power generation, we should have 2000 hour top of 2000 will come somewhere here. So, 2000, this is the line for 2000. So, this is the energy which has to be supplied by top of plant, and this is for the base plant, right. Now, the value, the plant which has cost C is minimum shall be the base one. So, this will be the base one, this will be the top of plant, right. So, now the base energy plant is this one and it will, and this plant B will run for 2000 hours only. Now, when it is running for 2000 hours, we can always find this value, how much power will be required. Now, in order to find that, so kilowatt of base, you can draw it here. So, this is 8760, this is annual 8760, this is 2000, this is 5000, right. So, this kilowatt is going to be equal to base by, now this is 67 8760 minus 2000, 6760 is equal to 5000 divided by 8760. So, this will give the base kilowatt. From here we will get the base kilowatt, and the base kilowatt is 5000 multiplied by 6760 divided by 8760, and the base kilowatt is going to be 3860 kilowatt, right. So, now we have the base kilowatt also, this is 3860 kilowatt. Now, for this part of the triangle, 5000 minus 3860 is equal to 1140. So, this part is only 1140. So, the capacity of this is required is 1140 kilowatt, capacity of the base load plant, peak load plant is 1140 plant, capacity of the base load plant is 3860 kilowatt. So, now we have decided this, right, for the optimum value. Now, the cost of generation. So, for peak load plant, what is the cost of generation? The cost of generation is first of all, we will have to find how much energy is generated annually in the peak load plant. So, in the peak load plant, kilowatt hours, that is total energy generated, will be the area of this triangle. So, area of this triangle is going to be 1140 multiplied by base is 2000, 2000 divided by 2, and this will give the annual energy generation as 114 kilowatt hours. This much of unit, that is what I said, even 1 paisa makes a lot of difference, right. So, this much of kilowatt hour will be generated by the peak plant. Similarly, for the base plant, we can find either we take area of this or area of this triangle minus area of this triangle. Area of this triangle we have already calculated. So, area of the bigger triangle is going to be 5000 multiplied by 8760 divided by 2, and it is going to be 114 minus base plant minus this one, previous one, this, right, and this will give us 2076 kilowatt hour. Now, we know the output of both the plants, right. We know the output of this, we know the output of this, right. Now, after this, two things, rest of the information is already with us. We know the value of in kilowatts, it is 1140, 3860 for the base load and 1140 for the peak load plant, right. So, we know the value of kilowatts, what is the power generation capacity of both the plants, we know the annual energy generation also. Now, we can find the annual cost of station B and annual cost of station A. So, annual cost of station B that is base load, B is base load, right. It is going to be rupees 75 plus 5 into 3860. 380 is the peak is the capacity of the plant, plus 0.014 multiplied 2076, that is going to be equal to rupees plus 19300 plus 290640. So, just a difference of 0.1 paisa, you can see how much difference will show, I mean, just leave it. So, this is going to be equal to total cost as rupees 105,9940. Now, cost of generation of plant B, that is peak load plant. Plant A, that is peak load plant. Now, for the peak load plant, the cost is rupees plus 3 into maximum power generation capacity, that is 1140 plus 0.015 into 114, and that is going to be equal to rupees 620,520, right. And for this one it was 105,9940, right. So, total cost is going to be, total cost, minimum cost is going to be 105,994 plus 620,520 is equal to 168,0460. This is rupees. This is the total cost of energy generation, annual cost. This is the total annual cost. Now, you want to have cost of generation of per unit, right. So, this is the total cost. So, for per unit cost, again we will have to divide this by this area, right. So, the per unit cost is equal to total cost plus divided by the area of this triangle, 5,008,760. This figure 8760 is there because this is the total number of hours in a year, right. So, this is going to be half into 5,000 into 8760, and this is going to be equal to cost per unit as 168,0460 219 is equal to 0.0767 or 7.67 paisa per unit. This is how the cost is calculated, because if we take, in this case, if we take the entire generation by one plant, the cost will be high. If we take entire generation by A or B, the cost will be high. So, what we have done, we have taken part, this is a base load plant which has lesser value of C, that is the base load plant, and this is the peak load plant, right. And we have taken the combination of these two, and this has given the final minimum cost per unit energy generation. Okay. Next is, we will take another numerical. It is about the photovoltaic cell. Photovoltaic cell, we have taken already lecture on the photovoltaic cell. So, there is a photovoltaic cell. Photovoltaic cell is a device for direct energy conversion. Now, what happens in normal energy conversion? Energy conversion means converting available energy into electricity. So, there is normal energy conversion. So, for that what we do? We burn the coal, generate the power, right, power in the form of a shaft work, and that shaft rotates the generator, and that is how the electricity is generated. But here in this case, whatever available energy is there, it is directly converted into the electricity. So, that is why it is called direct energy conversion. So, there is a photovoltaic cell which has an open circuit voltage of 0.6 volt, right. Short circuit current is 250 amperes per meter square at a cell temperature of 40 degrees centigrade. Calculate the voltage and current density that maximizes the power of the cell. So, we have to find the voltage and current density, two things that will maximize the power of the cell. What would be the corresponding maximum power output per unit cell area? So, For this numerical number 2, we will start with the formula, the ratio between short circuit and IO is equal to exponential of E V open circuit divided by KT minus 1. Now, K is Boltzmann constant, right. So, it will remain constant. So, this is going to be equal to exponential of this E is charge on an electron, that is also constant 1.602 into 10 to power minus 19. VOC is given, that is 0.6 volts. So, here we will write 0.6 volts. Boltzmann constant is also given, it is 1.381 into 10 to power minus 23, right, and temperature in Kelvin. So, 273 plus 40, it is going to be 313 minus 1, right. So, this will give the expression will be as 4.544 into 10 to power 9. Now, reverse saturation current density IO by AC. It is equal to ISC by AC divided by ISC by IO. We have simply manipulated this ratio. IO by AC, it is ISC divided by AC, ISC divided by IO. So, IO will go up. So, then again if you simplify this, you are going to get this expression. Okay. Then ISC by AC is given 250, it is given here 250. So, this is going to be 250, right, and ISC by IO, this we have just now calculated, it is going to be 4.544 into 10 to power 9, and this will give the final expression as 5.502 into 10 to power minus 8 amperes per meter square. This is IO by AC. Now, again we will use the formula, I will take them 1 plus I have derived all these formulas in my lecture on the photovoltaic cells, right. So, from this we will simply put on the values, it is going to be equal to 1 plus 1.602 into 10 to power minus 19 Vm, Vm is not known, divided by K 1.381 into 10 to power minus 23 into temperature 313, right, and EXP exponential of again E voltage on an electron 1.602 10 to power minus 19 Vm divided by K 1.381 into 10 to power minus 23 into 313 is equal to 1.4544 into 10 to power 9, that is this one. Now, here only unknown is Vm, right, and in order to find the value of Vm, we will have to use the trial and error method, because it is in exponential form here. So, by trial and error, we get the value of Vm as 0.519 volts, right. Now, after this Vm is known, now we have to find the value of Im. Now, Im is equal to EVm by kT divided by 1 plus EVm by kT, I short circuit plus IU. Now, again we will keep on putting the values. E is equal to 1.602 into 10 to power minus 19. Now, the value of Vm is also known to us, 0.519 divided by kT. K is 1.38, 1 into 10 to power minus 23 into 313, right, divided by 1 plus again 1.602 into 10 to power minus 19 into 0.519 divided by 1.381 into 10 to power minus 23, and T is 313. Right, and this will give the final expression as, so this is going to be equal to 237.6 ampere per meter. This is Im by AC actually. This is not Im, this is Im by AC. So, Im by AC is equal to EVm by kT divided by 1 plus EVm by kT ISC plus IU, right. Now, here we will keep on putting the values, 1.602 into 10 to power 19 minus 19, Vm is 0.519 divided by K is 1.38 into 10 to power minus 23, and T is 313 divided by 1 plus 1.602 into 10 to power minus 19 into 0.519 Vm divided by again K 1.38 into 10 to power minus 23 into 313. ISC plus IO is 250. 250 is already given somewhere, 250 plus 5.502 into 10 to power minus 8. Now, this will give the final expression as 237.6 amperes per meter square, right. So, that is the current density. So, maximum power is equal to Im divided by AC into Vm is equal to 237.6 into 0.519 is equal to 123.3 watts per meter square, right. So, after this we will take another numerical, this is a short numerical. It is about the motors of an atomic icebreaker which deliver 30 megawatt. Calculate the fuel consumption of reactor per day if its efficiency is 22%. The reactor efficiency is 22%. Average fission energy released of uranium-235 nuclides is 200 million or molecules is 200 million electron volts. Find the quantity of 29.3 megajoule per kg. This is calorific value of coal, 29.3 megajoules per kg coal needed to obtain the same power if the efficiency of this normal thermal power plant is 78%. So, here power by icebreaker, right, is 30 megawatt, efficiency 22%. So, output is 30 megawatt, right, into 24 into 3600 per day. That is energy, and it is going to be 25.92 into 10 to power 11 joules. Now, input is going to be 25.92 into 10 to power 11 divided by the efficiency of the plant. The efficiency of the plant is 22%, right. So, it is going to be 0.22 and that is going to be equal to 11.78 into 10 to power 12 joules. This much of energy has to be generated in nuclear plant and that will be sufficient to meet the output of 30 megawatt. Right. Now, let us talk about how much fuel is required. So, 200 million electron volt per nucleoid. It means 200 into 1.6 into 10 to power minus 13 million, okay, joules, because 19 and this is actually it is 1.6 into 10 to power minus 19 into 10 to power 6, it is million, right. So, it is equal to 3.2 into 10 to power minus 11 joules. Now, if we take 1 kg atom or 1 kilomoles of uranium, right. 1 kilomoles will count around 235 kgs, right. In 235 kgs, how many nucleons will be there? This multiplied by 6.02 into 10 to power 26 by Avogadro number, and each nucleon is producing this much of energy, right. So, the total energy released is 200 into 6.02 into 10 to power 26 into 1.6 into 10 to power minus 13 divided by 235 is equal to 8.2 into 10 to power 13 joules per kg of uranium. Now, how we have done? I am repeating, one molecule is releasing 200 million electron volt, that is converted into the joules. 1 kilomole will consist of 235 kilograms of uranium consisting of this much number of molecules, right. And if we multiply this number of molecules by the energy generated per molecule and divide by 235, we will get the energy generated per kg of uranium. Now, for calculating fuel, that is coal. For coal, it is 11.78. Okay. Now, daily fuel consumption. Of uranium is 11.78 into what is that? 10 to power 12. 10 to power 12 divided by 8.2 into 10 to power 13. Because this 8.2 10 to the power 13 is the energy released per kg of uranium, and this is the total amount of energy which is required. So, total amount divided by the energy released per kg, and it is going to be equal to 0.1436 kg, 143 grams, 143.6 grams. Now, for coal, efficiency is 78%. Daily energy is equal to how much? 25.92 into 10 to power 11 divided by 0.75. So, sorry, 78, not 75, 78. So, daily energy input is going to be equal to 33.23 into 10 to power 11 joules, right. Now, coal required per day, total energy requirement (113.4 tons). So, you can compare the quantity of fuel required here. They only require 143 grams of uranium to produce the same power, and for matching the power we need 113.4 tons of coal, right. That is all for today, right. Thank you very much.